Hello everyone. The title of my presentation is A New Approach on the Fractional Modeling of Complex Biological Systems. The outline of this presentation is as follows. In the first section, we give a brief introduction about the classic form of fractional derivatives. Then, we introduce a new fractional operator with Mittag-Leffler kernel. In the next section, we define fractional differential equations with Mittag-Leffler kernel. Then, we provide a new fractional model of tumor immune surveillance. We give some simulation results to verify the theoretical analysis. And finally, we close this presentation by some concluding remarks. Let us start with the definition of Riemann-Liouville derivative. For alpha between 0 and 1, the classic form of Riemann-Liouville derivative of order alpha for a function f is defined by equation 1. Concerning Caputo derivative, we give the next definition. The classic form of Caputo derivative of order alpha for a function f is defined by equation 2. For alpha between 0 and 1, the relation between Riemann-Liouville and Caputo derivatives is given by equation 3. If C is a constant function, then we can compute Caputo and Riemann-Liouville derivatives of a constant function C as given by equation 4. Regarding a power function for alpha between 0 and 1 and p greater than 0, we have relation 5 for Caputo and Riemann-Liouville derivatives of a power function. The Laplace transform of Caputo fractional operator of order alpha is given by equation 6. Now, we introduce a new fractional derivative with Mittag-Leffler kernel. In reference to a new fractional derivative with Mittag-Leffler non-singular kernel was suggested by Professor Atangana and Balianu. For alpha between 0 and 1, the AB fractional derivative in the sense of Riemann-Liouville is defined by equation 7. Concerning AB Caputo derivative, we can say that for alpha between 0 and 1, the AB fractional derivative in the Caputo sense is defined by equation 8. In these definitions, the function b is a normalization function such that b at 0 and 1 is equal to 1. Also, e is the Mittag-Leffler function given by equation 9. There is also a relation between the AB derivatives in the Caputo and Riemann-Liouville sense, as given by equation 10. The Laplace transform of these fractional operators are given by equations 11 and 12. In the following, we define fractional differential equations with Mittag-Leffler kernel. For this purpose, consider a fractional initial value problem with AB Caputo derivative as given by equation 13. Using the Laplace transform, we can convert equation 13 into a nonlinear Volterra integral equation as given by equation 14. In this part, we talk about the existence and uniqueness of the solution for fractional differential equations in the sense of Mittag-Leffler kernel. Let f be a real-valued continuous function defined in the domain G of a plane T and Y, satisfying the Lipschitz condition. Then there exists a unique solution Y of the fractional initial value problem in the sense of AB Caputo derivative with Mittag-Leffler kernel. As an example, please consider linear fractional differential equation 17. The function defined by equation 16 is the solution of this initial value problem. For alpha equal to 1, the problem 17 takes the form y' equal to lambda y. Hence, it has the classic solution as in equation 18. In the next section, we provide a new fractional model of tumor immune surveillance. According to the AB Caputo derivative definition, a generalized fractional model of a tumor immune surveillance system is provided. In this new formulation, the interactions between tumor cells and immune response are modeled by a system of fractional differential equations involving non-singular AB Caputo derivative operator. A predictor-corrector numerical procedure is also applied to solve the tumor immune system related fractional differential equations. Here you can see the model of tumor immune surveillance system by using AB Caputo derivative operator. Now we give some simulation results to verify the theoretical analysis. Figure 1 shows the growth of tumor cells dynamics for different values of alpha and 3 different fractional operators, namely classic Caputo, Caputo-Fabrizio, and AB Caputo. As can be seen in figure 1, the populations of tumor cells grow exponentially. However, they exhibit different asymptotic behaviors for different values of alpha and different choices of fractional operators. In addition, the responses within all fractional models tend to the integer response as alpha goes to 1. Figure 2 shows the growth of tumor cell population by three different fractional models with alpha equal to 0.9 and the experimental data of tumor growth used in reference 5. Comparative results in figure 2 show that the AB Caputo model with alpha equal to 0.9 is agreed very well with the real data in the whole interval. Finally, we close this presentation by some concluding remarks. Motivated by the fact that memory effect has various behaviors, the researchers tried to suggest several new fractional derivatives to describe more accurately these phenomena. Recently, a new fractional derivative with Mittag-Leffler kernel was proposed and applied to some interesting real-world models. In this research, we investigated the existence and uniqueness analysis for the nonlinear fractional differential equations with AB fractional derivative. We also examined the interactions between various tumor cell population and immune system via a system of fractional differential equations involving Mittag-Leffler kernel. Comparative results verified that the fractional model with Mittag-Leffler kernel and alpha equal to 0.9 has a good fitness with the real experimental data in the whole interval compared to the other fractional and integer order models. Consequently, the new aspects of fractional calculus provide more flexible models, which help us to adjust better complex dynamical systems. Here you can see the references of this presentation. At last, I would like to thank you very much for your attention.